With Asana, you can manage any kind of work, from project intake to campaign management to strategic planning or anything else your team works on. Asana works for you. Try for free today at asana.com.
Ready? Hello, everybody. Hello. I appreciate everybody being here. Welcome to the stream once again, the early stream here on this beautiful Saturday, April 26, 2025. Feeling good today. I hope you are as well. Welcome to the stream. I hope everybody's having a wonderful day. Welcome in, welcome in. Let's get that desk fixed. There we go. That looks good. All right. All right, so we got a pre-stream page kind of loaded up with chat going in there, so pretty cool. And then we got the subscriber count here in a new formatting. I applied some custom CSS to it, and what do you know? Bada bing, bada boom. Look at that up there. Cool. So I wanted to have it originally update color per every change of sub, but that was kind of... it wasn't really possible because it didn't really allow for updates, like live refreshes or whatever. So, or I'm not sure. So I just did it. So I just keyframed it, but it's pretty cool. Let's go ahead and elongate that here. Let's make it. Yeah. All right. Nice. 1.81K. Yes. I appreciate everybody for the kind words. Thank you so much for everybody's support here as we're growing up rapidly. 1.81K here. Little by little, climbing up the board. So I appreciate everybody's support as we learn here. But truly, this is about everybody learning together through various means. So whatever it takes, as long as you're working on something on the side or following along on the stream directly, you're putting in those hours, which is really important, which is honestly the hardest part about all of this, is just sitting down and actually doing the work, as I bet you probably you come to realize yourself. So thank you truly everybody for being here once again. My name is Michael. I'm 26 years old. I got a degree in human biology and a minor in chemistry. I've been teaching myself Python and programming more generally for about 10 months now. And we're currently working on a project and a few projects, I guess. We have an open source project right now that we are currently, building live with everybody on the stream. We're going to go over the pull requests today. I think we have one that we're going to try to merge into dev and test out how it works. So pretty cool that we got some contribution from the community. So really awesome. We'll give a shout out to that said person, and then we'll also add into the development branch a contributors .md markdown file where we'll add in all the contributors, and you can have a little special message or whatever in there if you would like. I'm not sure. So yeah, we'll have to do that. Pouring some C4 energy drink. Speaking of drinks, let me go ahead and grab a little drink. Let me go get a drink. I've got some Coca-Cola here for today. I'll be right back. All right. Welcome everybody again. It's awesome to have everybody here. We got Miss Kitty here. We got Miss Sky here. Everybody's here enjoying the stream together on this Saturday. All right, let's get going here. What do we want to work on today? That is the question of the hour. What do we want to work on? So, what to work on? What to work on? Should we warm up with the Leet code or should we do some reading, you guys? I've revealed the dog on stream before. What should we do? You guys choose Leet code or do some reading. I know we've been doing. I've been, kind of absent on the reading, so we could break open, DSA and Python and keep reading. We have three options. We could keep reading DSA in Python, Fluent Python, or Fluent Python or ProGit. So ProGit, we're on chapter 7. We're almost done with the whole book. So I feel like we haven't done reading, so we're due for some reading. What do you guys think? But I'll let you guys decide. Come here, Sky. Come here. Come here. It's okay. It's okay. Come here. That's a good girl. Here is Miss Sky. Oh, she's kind of she looks funny from this angle, but yeah, she's my what are they called, not Nightwalkers, what are they called in Game of Thrones with the blue eyes? I got her right before I went to college, my freshman year, and she's been my buddy ever since. She's traveled with me to every state I've been in, every apartment we've been together in. So she's been my my buddy, my little partner in crime here. Then we rescued Miss Kitty a couple years ago. Alrighty, let's lower this. Alright, what do you guys want to get into? What do you guys want to read? Let me know in chat. Do you guys want to read or do Leet code? We haven't read in a while, so bear that in mind. Should we do some reading to, break up to keep along and keep going, chugging with our learning? Hold on. What happened to the tunes? There we go. All right. Got my Twitch feed thing set up here. Going full streamer mode here, boys. Let's see, do we need to edit? No, looks good. Alright. We're going full streamer mode. Community poll to burn the Git book. ChatGPT is my Git resource. I'm trying to read some Python, burn the Git book. It was getting pretty tough, huh? It was getting pretty tough to get, not even in terms of content, but just like, man, like what? This book is just like, do we really need a book on this? It was, yeah. Okay. My hair looks so goofy. Oh, okay, we gotta get going here into the stream. Ah! We gotta get going here into the stream. We gotta get started. Okay. Let's get going here. You guys aren't following on the Twitch, make sure to go hit that link in the description and follow along on Twitch. We recently got affiliated with Twitch, so hopefully, I don't know what that will bring. Just signed up for it. It's like, all right, whatever. So we'll see what happens now on there. Okay. Yeah, no haircuts in this economy, right? Okay. I usually get charged for, female haircuts because my hair is pretty long by the time I cut it. Okay. I think we need to read. Like, honestly, I know it's not the most entertaining thing of all time, you guys, but we need to get in. We need to keep going with our reading. So let's go with... people like the DSA, you know. Okay. Well, the thing is the chat might make it difficult here. Okay. SS Low, those follicles be hanging on for dear life, let me tell ya. Don't get it twisted. It's hanging on for dear life. But the thing is the chat kind of gets in the way, so I might need to move chat. Which kind of sucks because I wanted to keep it there, but whatever. We'll move it. Down to here. Okay, let's get into this. Okay, we got a couple. Let's do 3 reinforcement problems and then we'll read for 15 minutes. 15-20 minutes, and then we'll move on, okay? Let's get going here. Let's do... I haven't done reinforcement problems in a while, so how did I do this last time? I just did chapter 2, keys. Okay, so we'll go chapter 10, keys. Then we'll do chapter 10, notes. We'll take all of this and put this in chapter 10, notes. Now we'll go into here, chapter 10, keys, and we'll make a R10 .1 key.py.
No matter how you travel, it's good to have.
No!
Some people plan every minute. No sleep, bus, music.
Okay. So, give a concrete implementation. Right? Give a concrete implementation of the POP method in the context of the mutable mapping class, relying on the 5 primary abstract methods of that class. Give a concrete implementation of the POP method in the context of the mutable mapping class. So mutable map. Give a concrete implementation of the POP method in the context. What does that even mean? Subcount RGB. Yeah. What does that even mean? Give concrete implementation of the items method in the context. Maybe not. Maybe we might just go to the reading. Chapter 11. Oh boy. This one was a hard chapter. It's gonna take some more thorough investigating. Okay. Let's get into this. That was rough. Okay, this is gonna be good. Search trees. We need this one for sure. Okay, we'll go chapter 11, search trees. Okay, let's get into this. Number 11.1. Binary search trees. I'm gonna change the title of the YouTube to have DSA in it so people know we're doing DSA. If you're on the stream right now, go throw a thumbs up on the stream. We got 3 thumbs up right now, 7 people in here though. Go ahead and hit a thumbs up on the stream if you'd be so kind. Appreciate you guys. It really helps out. We'll go DSA plus project. Okay, there we go. Hey Aljo, Algo, Algae, Algae, oh my gosh. How's it going? Welcome. We'll work on the project a little bit later. Yeah, we're just getting back into our reading here of DSA. We're on chapter 11 of data structures and algorithms in Python. We got to keep going here. We're almost done with the book. We got to keep chugging along here. Okay, chapter 1.1, and then we have 11.2 is balance trees, search trees. This will be good information here. All right, 11.1, binary search trees. I'm gonna turn down the music just a little bit. In chapter 8, we introduced the tree data structure and demonstrated a variety of applications. One use is a search tree, as described on page 332. In this chapter, we use a search tree structure to efficiently implement a sorted map. The 3 most fundamental methods of a map M of section 10.1.1 are the map at index of some key, return the value v associated with the key k in the map M, right? We know that's basic. If one exists, otherwise it raises a key error. Map at key index equals v, associate the value v with the key in the map M. We know that one too. And then delete, right? Map at index key, remove the map from the map the item with the key equal to the k. If M has no such item, raise a key error. The sorted map ADT includes additional functionality, see section 10.3, guaranteeing that an iteration reports keys in sorted order and supporting additional searches such as find _GT, find greater than. Let's move this up here. So. The sorted map ADT includes additional functionality. Section 10.3, guaranteeing that an iteration reports keys in sorted order and supporting additional searches such as the find greater than at that key and find range start stop. The binary trees are an excellent data structure for storing items of a map assuming we have an order relation defined on the keys. In the context, a binary search tree is a binary tree T with each position P, storing a key value pair KV, such that keys stored in the left subtree of the position are less than the K, and keys stored in the right subtree of the position of the P are greater than K. Okay, so in the context of a binary search tree, is a binary tree T a binary tree T with each position P storing a key value right, such that keys stored.
Driving through the country. New
Oh,
vacation
come on.
home, newly expanded business. I know what you're thinking. This only happens in dreams.
This is Data Structures and Algorithms in Python. You can find all these books I'm reading and everything for free in my Discord linked in the description below. So feel free to check that out and join. Where we work on community open source projects, share resources, answer questions, all that jazz. Thanks for coming in, Algo. Keys stored in the left subtree of P are less than K, right? And then keys stored in the right subtree of the position P are greater than K. Okay, an example of such a binary tree is given in figure 11.1. As a matter of convenience, we will not diagram the values associated with the keys in this chapter, since those values do not affect the placement of items within the search tree. So the value is 44. 17 is less than 44, so it gets placed to the left. 88 is greater than 44, so it gets placed to the right. Now this is a root node in itself, so 8, 32, 65, 97, 54, 82, 76, 80. 93, 32, 28, 29 goes off to the right. That's bigger, so it goes off to the right, right? We've done problems like this in Leet code. So I'm going to take this diagram here. We're going to go a little bit closer to the edge here. Would have been good, but no cigar. One more try here. There we go. Let's take this diagram, copy the image, and we'll paste it into the example as such here. Navigating binary search tree. We begin by demonstrating that a binary search tree I can never pronounce it. Hierarchical. This word is so hard for me. I don't know what it is. My northwestern accent can't do it. Hierarchical represents the sorted order of its keys. In particular, the structural property regarding the placement of keys within a binary search tree assures the following important consequences regarding the in-order traversal of the tree. Proposition 11.1 states that an in-order traversal of a binary search tree visits positions in increasing order of their keys. Justification. We prove this by induction of the size of a subtree. If a subtree has at most one item, its keys are trivially visited in order. More generally, an in-order traversal of a sub or tree, right, consists of a recursive traversal of that possibly empty left subtree, followed by a visit of the root, and then a recursive traversal of the possibly empty right subtree. Yep, just basic, right? This would go first in order. It would go to the left if there is any, and then if there wasn't, it would go to the right if there is any. Okay. By induction, a recursive in-order traversal of a left subtree will introduce an iteration of the keys in that subtree in increasing order. Furthermore, by the binary search tree property, all of the keys in the left subtree have keys strictly smaller than that of the root. Exactly. So if you go 44 to 17 to 18, then you go to 32 to 28, then you record 32. But this has a left, so the left comes first, so 28, 29, then you record the 32, so then you go to the 88, but you don't record it, it has a left, so you go left, you record that value. So what you would do is you go all the way left as much as you can, record, go back, okay, I can't go left, I go right, oh, I can't go left, can't go left, I go right, boom, that's my next high, or this would be my next highest value is 28, take it, I go right, take it there, I come back up. So I would go 8 to the 17, to the 28, to the 29, to the 32, to the 54, to the 65, to the 76, to the 80, to the 82, to the 88, to the 93, to the 97. That would be the process of the in-order traversal. Okay, so an in-order, just remember this, an in-order traversal is a traversal of a binary tree where the binary tree is in order of its, keys of increasing order. It's an ordered binary tree, a binary search tree, right? Has these properties. Keys are stored with left or less than their root, and keys that are greater than or right of the root. Since an in-order traversal can be executed in linear time, a consequence of this proposition is that we can produce a sorted iteration of the keys of a map in linear time, which represents it as a binary search tree. Although an in-order traversal is typically expressed using a top-down recursion, we can provide non-recursive descriptions of operations that allow more fine-grained navigation among the positions of a binary tree relative to the order of their keys. Come on. Okay. Our generic binary tree ADT from Chapter 8 is defined as a positional structure, allowing direct navigation using methods such as a parent of P, left P, and right P. With a binary search tree, we can provide additional navigation based on the natural order of the keys stored in the tree. In particular, we can support the following methods akin to those provided by a positional list. First, returns the position containing the least key, or none if the tree is empty. Last, return the position containing the greatest key, or none if the tree is empty. Before, return the position containing the greatest key that is less than the position P. Or after that position, return the position containing the least key that is greater than that of the position P. The first position of a binary search tree can be located by starting a walk at the root and continuing. So let's pull up our thing here in display mode so we can see our picture and walk through this. The first position of a binary search tree can be located by starting a walk at the root and continuing left to the left child as long as a left child exists. So we're on our root, if left, go left. Okay, if left, go left. If left, go left. Okay, no left. Okay, so this value is then returned. That would be returned by, right? So if right is, so this would be the first, walk in the route and continue to the left child as long as the left child exists. By symmetry, the last position, so for last, you would go right. This is our greatest. There's no more right positions. So the algorithm for after, right, for after P, if I want to say what is after the root position, it would give me this position here. So I'd say if right position is not none, then you would call walk equals right on P. So you would move to the right on P, which houses walk, while left, walk is not none, do walk left, return walk. What? So if right is not none, then you walk, you move the position to the right. If there's a left, you continue walk left until there's none. Why would you walk left on an after? So what if we call after this position here? Successor is nearest to ancestor having P in the left subtree. So you walk to the right as far as you can. Oh no, you just go to the right after. If there is a left, you go left all the way. Oh, got you. So if we want to say what's after 44, well, what's after 44 is 54. So we have to go right initially, right here, which is captured here. So walk is captured on 88. And then we say while there's no walk, while we can walk left, walk left. So we'll go boom, boom. Now walk is overrode as 54, which is the next number after 44. And so we'll return walk there, right? So if there is no value greater than to the right, else the nearest successor is in the left subtree. Right, so let's say that there is no value here. But let's say there's a large value over here of 54. So then it would go here to the left. You would walk equals the current position. Ancestor, you would call parent of walk. While ancestor is not none. Successor is in the nearest ancestor having P in its left subtree. What helps with me in these is when we look at those, when we look at one of these, we can just realize the same logic is applied to all. So going through every manual position could just make these things more complex. Yeah. It's a good point, Max. Thanks for coming in, dude. Okay, the rationale for this process is based purely on the workings of an in-order traversal given the correspondence of Prop 11.1. If the position has a right subtree, that right subtree is recursively traversed immediately after P is visited. So if the position 44 has a right subtree, that right subtree is recursively traversed immediately after that position is visited. And so the first position to be visited after P is the leftmost position within the right subtree. If the position does not have a right subtree, then the flow of control of an in-order traversal returns to the position's parent, right? So let's say that we're trying to find a value, let's say there is no right subtree on 88. It would go to here, to the parent, then the parent subtree traversal is complete. Okay, so return to the parent. If position, okay, hold on, where was I? Sorry. If the position that we're currently on does not have a right subtree, then the flow of control of an inward traversal returns to the position's parent. If position were in the right subtree of that parent, then the parent's subtree traversal is complete and the flow of control progress to its parent and so on. Once an ancestor is reached in which the recursion is returning from its left subtree, that ancestor becomes the next position visited by the in-order traversal, and thus is the successor of the position. Notice that the only case in which no such ancestor is found is when P was the rightmost last position of the full subtree, in which case there is no successor. A symmetric algorithm can be defined to determine the predecessor of a position before position, right? At this point, we note that the running time of a single call to after or before is bounded by the height of the full tree, because it is found after either a single downward walk or a single upward walk, while the worst case running time is O of that height. We note that either of these methods run in O of 1 amortized time. In that case, in that series of n calls to after P, starting at the first position will execute in the total of O of n time. We leave a formal justification of this fact to exercise C1134, but intuitively, the upward and downward paths mimic steps in the in-order traversal. A related argument was made in the justification of proposition 9.3. Interesting. So let's take this. Let's go here. Let's say, can you break this down with an example? This is the node before a given position, right, is a predecessor, like a binary tree. The after, this refers to finding the node after a given node of position, and the before refers to finding the node of the previous before the given position. The full tree, a binary tree in which every node, non-leaf node, has two children. And then a height is some h, right? After finding the predecessor before P, or the successor after P, can be done by walking either downward or upward on the tree. The running time for each individual call to before P or after P is bounded by the height of the tree. This means, in the worst case, it will take time proportional to the height of the tree, which is O of h. Amortized time, right? While a single operation like before P or after P takes O of h time in the worst case, like we talked about here, amortized time means that if we perform a series of operations, the average time per operation can be much smaller. So specifically in this case, the amortized time per operation is O of 1 when a series of n calls is made. This is because the total time for n calls grows linearly, O of n, not exponentially, even though each individual operation can take O of h time in the worst case. Imagine we have the following binary search tree of 50, where 30 is less than 50, so it goes to the left, 70 goes to the right because it's greater, 20 is less than 30, so it goes to the left, 40 goes to the right, and then 60 goes to the left because it's less than 70, and 80 goes to the right because it's greater than. So the height of this tree is 3, 1, 2, 3, because the longest path from the root 50 to its leaf is 3 edges. 1 edge, 2 edge. So the height differs from depth by -1 then. So if you have a value, you have a height of 1 but a depth of 0, right? This is depth of 1 but a height of 2. And this is the depth of 3. This is our surface, so there is no depth really. Or is our surface that's like up here, and this is considered depth of 1, 2? Well, then depth would equal height, so that doesn't really make sense either. Hey, we got a follow on Twitch, Testicles11. I like that name. Welcome. Thanks for following me here. Oh boy, we got another naysayer in the comments here, Mr. Zola. It's been working pretty good so far, my friend. So, after the call to after P or before P, let's say we're starting at the node with the value 30. Call to after P. So we're trying to find a node, the after call to 30. From 30, we would move downward to the right child, 40, as 40 is the next value after 30 in the in-order traversal. This operation takes O of 1 because we can directly access the right child of 30 without needing to traverse the entire tree. We just go right from 30 directly to the right, which would be its greater value. We call to before position P, find the previous node. From 30, we would move upward to its parent 50, and then move to the left child of the 50, which is the 30's predecessor. Okay, so you'd have to move up to its root and then to its left child. So wait. From 30, you would move upward to its parent 50, and then move to the left child of 50, which is 30's predecessor. If we had reached 30 from the right child of 50, we could move directly left, as 20 is the predecessor. Oh, because you need to go to the root value to check to see if this node here is a right node. Because if it is a right node, there's a value less than it in the root's left tree. And you have to find that value. Because this already is a left node, it would just go up to 50, travel back down to it, travel back down. There's its predecessor, and it would return that value. Interesting. If you perform a series of operations, let's say n calls like before P and after P repeatedly from one position, the total time across these calls will be proportional to n, even though each individual call could take O of h time in the worst case. If we have a total of n operations, the average time per operation will be O of 1, because over the course of n operations, we only traverse each node once for a small number of times, and the total time will scale linearly with n. Why does this happen? The reasoning behind the amortized time is related to in-order traversal. In an in-order traversal of a binary tree, you visit each node once, so the series of after position and before the position calls follow a similar pattern. For each call, you move through the tree's nodes in a predictable, non-repetitive fashion. And each individual call to before P or after P may take O of h time, in the worst case, due to walking up or down the tree. Okay, got you. Interesting. That makes a lot more sense. Okay, so because you visit each position once, now my question is, when you traverse back up in a before P call, you will, in your example, you travel then again, calling left with that position, which lands back on the previous or starting 30 node. Would logic be baked in here to either return the left of 30 if left of 30, else return 30, else return none, as 30 would be the least. Great question. You're right to notice that when you're traveling up the tree in a before call, you might revisit nodes like the starting node 30 in our case. Let's break down the logic in more detail and clarify how the algorithm handles this situation. What happens in the before call? When you're trying to find the predecessor of a node, you are essentially trying to locate the last node visited in an in-order traversal that comes before the given node. Steps for the before p function. If the node has a left child, like node 30, the predecessor in the rightmost node in the left subtree, this would be the largest value smaller than 30. So you go to the left child, 20 in our case, you continue going down right until you can go no further. But 20 has no right child, so 20 is the predecessor. If the node does not have a left child, you travel to the parent, check if it has a right child or left child. You're right to noticing that traveling upward might lead to the backtrack to node 30, and this is a critical point in handling the predecessor search. The key logic here is that when you return to the node 30 while traveling upward, you won't revisit it as a predecessor. This is because you are looking for the smaller node than 30, and since 30 already has been checked, you need either to go left of 30 if it exists. In other words, after traveling upwards from 30 to its parent 50, if 30 is a left child of the parent 50, you would continue going to 50's parent if it exists until you find a node that has a right child of its parent. Once you found that parent is the predecessor. It's really going off here with the breakdowns. Okay, where are we at? When does this one end? 11.1.3. 11.2 is on page 475. We're on page... Okay. We'll pause here then on the reading. We'll move on. Testicles paused him. Alright, we'll pause here on the reading for right now. We'll move on to a Leet code problem. How about? Alright, let's let's just push commit this. Start chapter 11. Alright. Let's do a Leet code. How about, yeah? Yeah? All right. Number 18, what's 18? No, dude, we're not doing 18. I haven't even solved 15. Okay, let's go. Let's go to our solved here. Or no, we'll go back to problems, I guess. Difficulty. No, why did it take me away from that previous? If I go problems, and then it reformats to this old format, this new formatting, which is annoying. Let's go here, difficulty. All right, let's see here. What's the next problem up here? Didn't we already do this one? Reverse linked list. I thought I already did this one. Given the head of a singly linked list, reverse the linked list and return the reverse linked list. Okay, let's try it out. We've been doing a lot of linked list stuff lately. Let's see. Okay. Reversed linked list. Okay, here we go. Let's try this one out. So we're given the head of a singly linked list in the terms of 1, 2, 3, 4, and 5. And we want to return the reversed list. So probably return the head of the reversed list, so the new head. Okay, so we're given a list of 1, 2, 3, 4, and 5. Okay. We want to say, and what does our structure look like for the code is you have a value and a next, okay? So while node, okay, so while there's a node, what are we going to do? We're going to so initially we need to take the starting node. So we need to take the head. We need to assign it to a none. Okay, so let's back up here. So we need to take this 1. We need to assign it here in green to a none value. Okay. So then we're going to have to save. We're going to have to make a temporary variable that will then point to the 2. Okay. Which will then break this here. So we need to assign the initial to a none and then assign the temporary variable to that position here. We then are going to so our 1 is pointing to our current node is pointing to none, and we have a temp node pointing to 2. So we then need to so we have a node pointing, our initial node pointing to none, and then we have a temporary node that we made that's pointing to here. Lost all that data. Okay. So then let's back up. So we assign the first value to none. The first node goes to none. We then move on. We then go in We then go in, we land. Do we want to move forward at that point in time? After we assign the first value to none, well, we're going to lose the path downwards here. So we need to have temp, right? We need to have a temp be put in between here,
Meet Asana,
which will
a
point
work
to the
management
2.
platform that helps companies get more done and save more time. Teams can stay connected while they track
We then
updates
need to
and visualize
pass in
timelines. Asana, a smarter way to work. Try it for free today at asana.com.
the previous node, right? And save this as previous. So we need to pass in the previous node. Temp. Pass in the previous node. And then so we need a helper function that takes in a previous and a current. Right? And then what it's going to do is it's going to take the temp node, which is pointing at the next node in our list. Hey Zaid, honestly just kind of jumping around, but following kind of similar structures. I'll cherry pick ones that I think I can do. So we need to pass in the previous node. We need to keep reference of that node. So we need a previous node variable. Okay, so let's think here. Let's go. Okay, so for this one, let's think and say. So we take the head node. We assign temp is equal to head, right? We then say head dot next is equal to none. Right. That'll take the head node 1 here, save it as temp for a copy, and then override its next value for head as none. So now 1 is pointing to none. And we have temp saved here as head as a reference to our start. Then we'll say while temp so we'll say previous is equal to none here, but previous is equal to So we say temp is equal to head, and then head.next is equal to none. Previous node is equal to none. So let's just do a helper. So we'll define a helper function here, which takes in a previous and a current. right? So so the previous takes the current node. So it's going to, what do we need this function to do? Take the current node and save ref of its next, and then reverse its next to point at previous. Okay, so what we're going to do is see the ref on its next temperature. So go next node is equal to current dot next, right? We're going to then say current dot next is going to equal previous return next node. So we're going to take the current node, get reference of its next node. We're then going to
Naloxone reverses an opioid overdose, even if you mispronounce it. For the record, it's naloxone. Like
So we're going to get reference of its next node. We're then going to assign the current node its next to previous and return the next node in the list. Okay, so what that means is we go, so we save so we're gonna go, so we're first gonna call helper. So I'm gonna define, I might have to put this above like this. So then we'll define, we'll go like this, we'll say helper, or it might have worked before, I'm done. Did it say self.helper? I don't think so. No. So we'll say helper, previous will be none. And then this little point to none, and then the current node will be head. So we'll say next node is equals to this, right? We call it once for none, and then we say while next node while next node, we will call helper on you gotta give it previous and then current. gonna return the next node. So there goes none. Next node is none. It's gonna go here. So we'll say while next node. Okay, so we have while next node. We're going to save the first value. So this is going, does it takes the, gets the next node of the current node, right? Says, okay, that's the next node that we're going to be on. Oh, next node. If node dot next. Say if node dot next, then we'll go ahead and run this. While next node, if next node. Infinite loop. While next node equals. So else will break. So we need to break out of the loop. None object has no attribute next. Let's try to take into current ahead of a blank list. So if current if not current, return if there isn't any value, just return current. This is messing with that initial function though. So we initially call helper here on next node on head if head is none. So you say if head, if not head, return head here, else we'll go here and do this. Doesn't even enter that. Okay, let's think here. Create an initial node. Should we create a node? So so if we were given a head node of 1, 2, 3, 4, 5, it's going to go to 1. It's going to take the node. So our helper function takes the current node and finds its next value, and then saves the current node's next value as previous, and returns the next node in line. So it'll take the 1, it'll take the 2 and the 1 given. It'll assign the 2 next node as 3. It'll take the 2, point it at the 1, and return the 3. So then the thing is we need to keep a reference of the previous. Return next node. What is this? Bruh. Minecraft movie? Come on.
Choose to lean into it. Every Mazda is engineered to give you effortless control.
Come on. I'm trying, Vivek. So, wow, next node. We take the previous. So we assign the next node to none. So while next node will continually call helper on next node. So we have while there is a next node, right? So we're on here, we have a next node. So initially we're going to move this and assign it to none and then move on to 2. That's what's happening here, is we're calling helper on the initial value with none to make it point at none, right? So what it's doing is it's calling helper with none as previous and the head as current. So then it's taking the previous, our head, and assigning it to none. So 1 goes to none. It's getting 2. So we need to return the next node, and we need to return the previous node. Right? return current node, next node. So this will do next node, current, and next node. So this is walk. Wow. Which is the preview. So this is going to spit out head as the current and the next node of head, which will be the 2, but the current is going to be pointing to that. Next node. Return the current node and the next node. And then, so while we have a next node, there is no next node, you stop and you return current. Current next node. So say if next node, and do this, else break. And then you want to return current. Infinite. Oh, shit. Ah, come on. Think. So I have a helper function. I have a helper function that will take a current node and a previous node, it'll take the current node's next value and save reference of it, override its next value as previous to reverse its direction, and then return back the next node in there. But if I return, so if I take the 2 for example, I reverse it, I get the reference of the 3, I reverse it to the 2, to the 1, then I return the 3 back. So then if we return, we need to initially kick it off, right? So if we turn, we have to do none for the initial one because the 1 has to point to none, which will be the current node, and then but if we call this recursively helper on initially none, no, this is going to return what's it going to return? We need it to return the next node, right? But then we lose, if I'm on the 2 here, I reverse the direction, I get reference of the 3, I save it, okay, 3 is up here, I break this bond, and I point it towards the 1, well then, I need to return this node and this node so then I can, because I need to return the previous node, so I need to return current node is next node and previous node is going to be the current, right? So we return those 2 values. But do we want to return this recursively on that? And so then can we call here return helper on none and then head here? And say if, so this would be, head none. So should we say though, if not current, return current. I could say like, whatever, we'll go back. Return, if not, what's this song? What is this? Come on. Okay, so then we return this, now what happens? String is blank. Head is a current. So what happens if we just return next node and current node as previous? Right. So we say while next, while head we'll call helper on so I say, well, we need to first call current previous is equal to head previous is equal to helper on none and on head and none. None, we return, so while head, call helper on head previous, turns back, head previous. This back none object. While there's a head node, continually traverse down, giving back the head in the previous as you reverse them. Current. If I take the 2 and I just put it, if I break this alliance, I have reference to here. I want to do this, go all the way down. Okay, so say if, or say if not head, not head, we return head. And do we not just return helper head and none? This will sign none. If not current, you return current. Type error. Hey Anshul, how's it going? Welcome, thanks for joining me here. I appreciate you for being here. How's it going? the thing takes forever to change color. It's kind of funky. Why is it doing that? Let's see if I can change it. We'll say it's instead of in. There we go, that should be better. Oh, it should at least fade a little bit more smoothly. There we go. Okay, so if there isn't a head node, then return the current. Given a head here. If there isn't a head node, then return the head node. Else the next node, right? Next head. Head is equal to head dot next. So this is returning 2 objects. I don't want to return 2 objects. So if I can return a tuple here, I'm calling return helper. So I need to call helper here to recursively call it on the head, right? And then return helper, just call it initially to cascade it down. So I'm doing the recursion in here, and then return the helper head on none. Because then this will return head on my base case here. blank list still. I put in a little CSS, so it kind of changed it, but it's like, oh, we just lost a sub. We just lost a sub. Okay, we're getting an empty list, so if not head, return head. Call helper on none. So next node is head.next. Head.next is now reassigned to the previous node. And then we return bro unsubscribed. Tough luck, huh? Yeah, the CSS kind of, so people keep unsubbing and subbing to see the CSS changes. Yeah, it's interesting. It's like I'm gonna turn up the speed to 15 seconds. So I'll cut it. There we go. Oh, I'm really close to solving this one. Come on. Okay, so we have the helper on head and previous. If the head node is none, right? Meaning that the next node, we're going to recursively call this helper. Hey Ray, how's it going here? Welcome, dude. Welcome. So maybe I just need to so if we have a helper, okay, so when I call this function on the head node, it's going to say, okay, the head node is not none here, so we're not going to return head. We're going to get the next node, so it's going to say, okay, the next node is 2, so that gets saved here. Then we save that the the current head is equal to previous, head next is equal to previous, so it reassigns this next to the previous. So now the 1 is pointing to a none in our first call. And then we call so what happens if we just actually instead call helper next node just to do it to the next? And then return the head node at the very end. So it just will do it throughout rather than returning at each step. Well, the helper node isn't returning anything, right? So we want to call helper next, right? And then return head at the end of this. Well, it's returning head actually, right? On each call. So we call helper next, and then it's recursively calling itself on the next node. So else we'll do that and then return helper next node here. Turn the value there. So then it gets called back. Still blank list. Oh, shoot. You guys have any any tips out there for this one? I feel like we're close, but just not quite there. I'm gonna grab a milk dud. I'll be right back. Yeah, I also read Twitch messages. What's up, Solaris? Your messages are popping up. It's merged. If you guys have any tips on where we should go from here, feel free, but try not to give any spoilers. I really like to try to solve these myself and learn from them. If you guys have any Chester's hot fries, these are the snack of the day. These are so freaking good. Let me know if you like Chester's hot fries out there. Well, I am using pointers. I'm using pointers to head and previous, right? Like left and right. Where my left is my previous and my right is my head. Yeah, the dollar store Cheetos. Yeah, these are so good. Economy hit me like a truck. Ah. Dropping Cheetos all over. That's probably a good take, Ramjack. I was getting confused myself. We'll invert this. We'll say previous, current, right? So if not current, previous will be current. Next node will be here. We call none and then head here, right? So if it's not current, we return the current. No, we need to return previous. Right, we return the previous because we're going to move down until we go back, until we go through. Yes! Woo, we got it! Ooh, 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 hey! Hey! Yes! I knew we were right there. We just were returning the wrong value. We need to return previous because we were moving current to the none after we go to the end of the original list, and we return the previous, which is our new head, and it shoots backwards. Woohoo! Yeah! Leave a like on the stream for that one. Chester's hot chip for you. Solaris, Chaz B. Anshul Roy, Tim, Hyran, Ramtech, hot chips for all you guys. Ray Butler, Vanch, VivTech, hot chips for everybody. Sorry about your ears. The MacBook microphone is pretty, like if I'm here and I talk normally, it's only like in the yellow, negative 20 dB. But if I really start to go, it really ramps up. You got an Anshul. I believe in you, man. All right, I'm gonna go get a refill on my drink. Oh, my puppy. What you doing here, puppy? What you doing, puppy? What you doing, puppy? You're a good puppy. Go back earlier in the stream if you want to see my dog. I showed her earlier. I'm gonna go get a refill on my Morris cup. Got it at the thrift store. Picked somebody, I think somebody probably had like an estate sale, and their pet, after they passed away, their beloved pet cup got donated. So I picked it up and I gave Morris a new home. All right. Nice. Puppy, that dog is the size of a 5'9" male. Well, she's a puppy to me, Tim. She is a puppy to me. All right. Let's see. Did this one... What was the speed of this one? It was fast. Okay, so this was the optimal solution. So this is just revisiting every node once, right? So this is linear time and constant space. I'm doing the so this is linear, so this is so time, so O of n, space is O of 1. Whoa, we got a $5. Woo! David, it's me. Welcome. Sorry, I remember you. What's going on, dude? Welcome back. I appreciate you being here. David is me. Congrats on almost 2K subs. Keep going. This whole time I went from day 17 to 25 of the course. We getting there. Nice, dude. What course are you taking, David? And why you're on a different account? Did you change your name, or are you just on a different account? Everybody give some likes and hearts in chat for David. Let me give David a... Can I give a reply here? Yes. 5 big booms for David's dead brother. No. For Daddy David. I like that. 5 big booms for Daddy David. Boom, boom. You guys seen that meme? Me and Tim always joke about that meme where he's like, oh, I'm so sorry about your brother, David. I'm sorry he passed away from COVID. 5 big booms for David's brothers. What? Thank you so much, David. You're so awesome, man. Oh, awesome. I really appreciate the love. Thank you for all your support, and thank you to everybody here. You know, take this opportunity, use this stream to your advantage. I stream every single day. I'm really good at holding myself accountable and getting myself to do this. I have no life, no social life. You guys are my social life. So honestly, if you guys are struggling yourselves with procrastination, with your own studying, homework, personal projects, personal goals, you know, take this 2 hours that I come on every single day to really, you know, focus on yourself and better yourself. You know, I found it to be very, very rewarding to learn programming, but learn whatever it is that you want to learn and just hang out with me, daily, you know, and do it alongside me as if we were just, colleagues in college and going to the study room and just working together on our various majors or whatnot. I really want this to be, you know, an opportunity for you guys to just come in, pop in, get your homework done, hang out, say hello, participate, learn if you do want to learn something from programming, and, you know, move on with your day. It's not easy to get yourself to come in every day, especially with all the distractions that we have today. And I feel like people were a lot more disciplined, and especially with their intellect. And I don't know, it's interesting to think about the idea of, were people smarter today or were people smarter in the past? And now, in terms of smartness, there might be different levels of, maybe people had, I think people in the past had very, very advanced expertise on niche subjects, whereas maybe today people have very more broad knowledge on a vast majority of subjects because of all the resources. But it's very interesting to think about. Sub 5 times on 6 alts to Mike. Thank you, Tim, and Mordecai. Appreciate you. Do you like the regular show? Is that what that's from? I stream every single day around 7 p.m. PST after my 9 to 5 job as a formulation chemist. So for those that are new, I have a degree in human biology and a minor in chemistry, and I work as a formulation chemist for a biotech company where I make biological controls that are used to diagnose like patients in hospitals and whatnot, and for advanced analytical testing. So that's my current job. Yeah, get off the coding with the boys. Exactly. Michael, trust me, you're ready for a job in this field. I think you should try. You can hang with these CS PhD students and software. Bruh, you guys are gassing me up too much. I'm gonna get in there and just get like deflated. Awesome, Ray. How's it going? Let me know what's your studying been like, Ray. I've seen you popping in you've been popping in fairly consistently. Are you in the Discord? And what's your goals here, Ray? Tell me more about you. It's like athletics is always better today. You think people are smarter today? Okay, got you. But it's just so crazy, like, I think I've been watching some clips on like Oppenheimer, like the fact that those physicists were able to just come up with that just off of theory, right? It's just so crazy. But I guess that's what everything is nowadays, right? From chips to... I got a Discord completely for free. Everything is completely for free. I want to give you guys complete access to my whole roadmap and hangout sessions. So completely for free, link down below in the description of the YouTube and in my profile on Twitch. I'm also streaming live onto Twitch right now, so if you guys can join there if you would like to as well. Let's go ahead and move this the YouTube, the chat back over to the top there. So we can see the code a little bit better here. The thing is, for me, it's like pretty large on my screen, but for you guys, it looks kind of small. Bro, dropping that 5 minutes of gold. There's a Discord I might join, to be honest. Einstein could hang in this era. He'd get wiped. What is that noise? Yeah, go ahead and join, man. I stream every single day, and just come hang out with me here. Yeah, on a Mac. Alright, let's go ahead and see if there's another problem here we can do. Hopefully we won't take too long on the next one. I'll probably do one more problem, and then we'll go ahead and take a lunch break. and then we'll come back for a part 2 stream where we'll work on our project, and then we'll work on our project. For those that are new here, because I'm a chemist, I built a thin layer chromatography simulator. So I built a couple projects before in the past. I built an inventory management for my CS50P project, for my and then I built a task tracker for just a independent project, and then I built for my CS50X final project, I built a full Python to Kinter GUI application that is the small business manager that I have demo videos on my channel that you can go check out for all these projects. So it's the small business manager, and I have a community version, which is you can find in the Discord as well, information on that, where we're currently taking pull requests and working alongside community members of the channel to further along that project after I have published it for my initial final project. So I'll just a little preview here of what's coming tonight. So if you want to come back tonight into the part 2 stream after I take a little dinner break after we do one more problem here, is the thin layer or TLC chromatography simulator, or paper chromatography simulator. So right now we're working on some styling in the front end of it, trying to get a front end going. But the back end and the actual algorithm of it is you can generate chromatographies and simulate chromatography as you would in a chemical lab as like a freshman or sophomore in general chemistry in college. So you have a solvent here in black that travels up at 100% constant speed, whereas these other compounds have a randomized retention factor between 0 and 1 that is indicated based upon is compounded or calculated, and what that entails then is you would calculate the retention factor on your own in the lab setting, but by pre-predicting it here, we can model these simulations ourselves and show what they would kind of look like beforehand without actually having to do it in the lab. So you can see that if this medium was fairly polar, this blue, green, and red molecule would have very similar polarity to the travel of this plane as it's traveling up with the solvent at a very similar rate, whereas this yellow looks like it's traveling at about maybe a 60% rate, this one maybe a 75% rate. And so if we go ahead and just do another random simulation here, you can see that looks like purple here is pretty slow, yellow here is pretty fast though, looks like maybe like a 90%, same here with orange or with red. So you can infer then that this yellow here is fairly non-polar, depicting against the polar medium here as these travel. So we're going to try to create a front end to mimic what's going on here. So if I go ahead and do a live server of my current front end, this is what we have right now that I've been building so far. So we have just an add compound button, and you get with some JavaScript a new description and retention factor box, and you can add up to 5 of them before the compound button is grayed, and then you can run the simulation at any point in time with the compounds, and you can also randomize the simulation and put in random numbers into these values that you have open, and then you can remove compounds, remove, and then once you remove the final compound, those become disabled. So that's what we currently got going on so far. So pretty cool. Now we got to just kind of link things up and get a display going for the actual posting of the plot and whatnot, but we'll get into that this afternoon or later this evening. We're going to go ahead and try maybe one more Leet code problem here. That's my project I'm building. Mike probably makes a fire sandwich. I am not the cook. I am a consumer. I'm a buyer. Let's say I do not cook. I just go get takeout. I'll cook maybe when I have kids and have to cook. I don't like it. That's pretty cool. Actually, I might try and replicate this if you don't mind. Yeah, it's really easy. Chemistry theory, you can honestly pick it up fairly easy. So just come. I highly recommend coming back tonight for the part 2, and we'll get into that. Hey, VCOM1, what's going on Twitch? Thanks so much for joining me. How's it going? Okay, so we've solved, I think, like 51, 52 problems so far. Okay, so we did reverse linked list, we did the happy number, removed linked list elements. Let's do this one. They have a lot of linked list problems in these Leet codes. Okay, So 203, remove linked list elements. If you guys are working alongside me, bust open 203. Let's do this one together here. I've never done this one, so we'll see how it goes. Given the head of a linked list and an integer val, remove and an integer value. Okay, remove all of the nodes in the linked list that has the node equal to that. Okay. Okay, so I guess we'll just do another helper function, right? And we'll give in so this will be to remove node, given some node. Right? And so what we're going to have to do is, given some node, we're going to have to take the node, get its next value. Okay, so I have to say next node is equal to node.next, and then we say so we actually need reference to this previous node, right? So we need to keep the previous and then the current. Remove, we'll say current node here. Given the previous and the current, you get the next node. You need to put the previous node to point to the next node. So previous dot next is going to point to the next node. And then that's it, right? You just continue forward. So we will, you pass in the previous node and the current node. You get the next value from the current node and save it as next node. And you take the previous node that's pointing, so the 2 here, if we're trying to remove 6s, we're going to land on the 6, call remove current node, and then say, with passing in the 2 and the 6, we're going to take the get reference as 3 is the next node. 2 will then point to 3, removing 6 altogether. Okay, so then what we can say is while head, if head dot value is equal to value, then we're going to call remove current node Okay, so actually we can do this recursively, similar to our last problem, right? So we'll say return we got to return start though, right? If not current, turn so if not current, we're going to just return nothing back, and so start is equal to head. We're going to call remove node on none and head return start. Okay, so we have this function here where we will remove the node if not current node return. So then we'll say if current dot value equal to value, so if current dot value equal to value, then we're going to swap, get rid of the current node. Previous, current, next node, and value here. So if it's not, what do we want to do if it's not? We want to just move on. Next node. So no matter what, we want to get a next node. So we'll put this up here, right? If the current value is equal to the value, then previous dot next equals to the next node, and we'll return remove node current next in the value from there. Non-type object has no attribute next. So if the current value so we need to call remove node on head dot next, right? And so then still sorry if you hear like a humming. Someone below me is like using a vacuum or something. I don't know what's going on. So if not current, then we're going to return, right, as our base case. Our next node is going to equal to current.next. If the current value is equal to value, then we're going to take the previous dot next and we're going to call remove on that value. So I need to have a condition here say, so if not previous, return if not or current. So it's still getting hit with this none type. So it has to be and. So if they're both not, then return. Non-type object, still, really. Next node equals current dot next. How can current is not none though, because if not previous and not current, return. How is this getting hit here if current So let's go, let's instead of returning values, so if not previous, not current, return current value previous. We're going to remove that node given it. Okay, so we have the remove node function, which will given a previous and a current will remove the node. So okay, so we're going to say if current value equals to the value, then previous dot next is equal to node next node. So the next node though is going to be equal to current dot next, right? So then we're going to leave it like that, and we're not going to do anything. We're just going to move on. And then what we'll do is we'll return the next node. So we can keep going, right? So then let's go say while head, right? Let's remove this here, right? While head, if head dot value equal to value, then we're going to call remove node. The thing is, I have to give a previous. Oh, that's the thing. So if head dot is not value, what happens if the head node is the value? We're going to remove it. Given previous node. Sorry if there's like a humming. It's like there's like something going on below me, you guys. I'm sorry if it's really annoying. It's annoying me. Okay, so the remove node will just take the previous node and the current node. Right, get the next value and then gap over the current node basically, and then return the next node. So in the case of example 1, it would hit the 6. We would pass in the 2 and the 6. It would write the 2 to the 3, voiding out the 6 altogether. So if the head value is equal to the value target, then we're going to call remove node on previous and the head value, right? But what is the previous? So maybe we should ask then. We should say then. So if head dot next dot value is equal to the value, meaning that the next node, right, is equal to the value. So if we come onto the 2 and see and peek at the 6 and say, okay, the next node is there, let's go ahead and then call so then let's go ahead and call but what happens if you just return none? So while head, if the next value is equal to the value, we're going to remove node previous gets yeah, so maybe we should like head dot next. So while you have a next value for none, like, right? So you'll stop one shy of the end. If the next value is equal to the value, then we're going to remove the, so we got to call currently the head. So let's say that next node is equal to head dot next, right? If head dot next, if next node dot value is equal to the value, then we're going to remove the next node given the head that we're currently on. This will return head equals to this now, and then we continue on. What we're going to do is return, before we start this, we'll say start is equal to head, and we're going to return start. Update head as the return value. Keep going. Infinite loop. Call remove node. previous doesn't exist, current is head, and we remove current, we just move the head to next. Okay, so this remove node takes from the previous and current node and passes over the current node by assigning previous to the next node, and then returns the next node. Right? So we save a reference to the start while there is a next node. So while the current node you're on, the head has a next node in front of it. So it'll stop on, after the 5 here, it'll stop. If it doesn't, right, if it doesn't, equal to it, then we need to move head equals to head dot next. It's a next node. So that'll fix our infinite loop problem. But none has no attribute next. So we should say if not head. Okay, so while the head has a next value, we're going to obtain that next value. If that next value is equal to the value indicated, then we're going to call remove node on the head previous. We have to pass in the previous. And remove the next node. So we're gonna get next node dot next. Head becomes none. So what happens if we say if head, what if I just say while head then? So that only removed 2 values. It moved to the next, then tried to detect the next current. So I need to, I did detect if I'm currently on a value I need to remove by passing in the previous. So while head, previous, current, next node. Next node equals head dot next if if the head dot value is equal to the value, then we want to remove this head node. So if thing is though, is I have to know I need a previous value. Right? If the previous doesn't exist, current is the head, and we remove the current, we just move the head to next. Okay, so we'll say if head is equal to start, then we'll just say head is equal to head.next. We'll say head is equal to none, right? So F will say next node is equal to if head is equal to start, then next node is equal to head dot next, and oh, hold on. If head is equal to the start, if the head is equal to the start, then we want to remove this node by saving start equal to head.next. Right? Else, we'll say and then we have to say that head is equal to start. Let's see. Else. Right, so if the head is equal to the start, then we save start equal to head.next, and then save head equal to start. Else, head is equal to remove that head, given let me just get rid of this crap. So if it's not equal to the start, it's equal to the value, but equal to the value not equal to the start, we want to just go crap, dude. So the thing is I'm conflicted on is we should be checking whether or not the node that we're currently on is the one we want to remove, or the node that is next is the one we want to remove. What do you guys think? Should we remove the node that we are currently on, or the one that is next? Because if it's currently, I feel like we have to do the one that is next, because so start equals head while head, right? Testicles, welcome back. So while head, if head.next is none, right? If the next value is none, we're on the last one. We definitely have to remove the next. Yeah, that's what I thought. That's what I was thinking. Okay. So while head dot next. So while there is a next head value, okay, if the head dot next, so we'll say, we'll first go ahead and get the next node is equal to head dot next, okay? If next node dot value is equal to the value we're looking for, then we need to remove the next node. So if next node dot next is none, then yeah, this is a linked list test. So if the next node's value is equal to it, so we're on the 1 here, okay, we say the next node is 2, okay? Does the 2 house the value? No. It doesn't have the value of 6 that we're looking for. So if the node does not equal to the value, then the head equals to head dot next, and we move on. Well, head, right? Next, and we continue the loop. So if we're on the 1 and we say, okay, the next value is 2, it's not our indicated value, we're going to say head equals head dot next and move forward. Okay. Now in the 2 case, while head dot next, so there is a next value, we're going to get the next node, which is 6. If the next node's value is the value, right? And the next node is none, then the head dot next will point to none. Else so if this 3, so else head dot next. So actually we don't need to say that at all, I don't think. Head dot next. Just say is equal to next node dot next. Okay, so if the next node on the 2, we're on the 2 here, if the next node's value is equal to the value, which it is, we're going to say that the head node's next value is actually going to skip over and be the next node's next value. So 2 will now point to the 3. And then it'll go continue. and then we say head equals head dot next. So now we're on the 3. Okay, now we go to the 4. Now we go to the 5. It has a next value. So, and the next value is the node, the value we're looking for. So we're going to point it to there and then move forward. Head.next doesn't exist because now so when you say here though, if head is none, turn break if none else head we'll say if head is none break is that how you write that? No. If head is none, break. Else, head is equal to head.next. So we say while head and if we say while head and head dot next. Okay, so that solved the 7 one, but not this one. Now we're getting an empty list here. Oh, crap. So we have head start here. Oh, we're not returning anything, that's why. Start equals head. So if you return start, I don't want to return start though because start gets saved ahead immediately. So this won't work. In the case of this 7 is landing on the 7. Then it's returning 7. We just return head. No. because we're wanting to return the start of the linked list. Do I need to create a reference and then point it to the head at the very start? So ref equals to a list node, and then we go ref.next is equal to head, and then return ref.next. So if the current node we're on, so while head, so if, what happens if head? So if head dot value is equal to the value, then what do we do? Ah, come on, think. It shouldn't be that difficult. This should not be that difficult. Ah! I think I need a dinner break. Ugh. After this problem, we'll take a dinner break. Remove elements from the linked list. I'm gonna back up here. A lot of edits here. Oh boy. I'm gonna back up to where I had my function. Here, right? So we'll say while node, while head, if head dot value is equal to the value, right? If it's equal to the value, then right, else we're going to call remove node on head next equal to value, call given the head next else. This is returning head, just a blank list. equals to create a reference node. Start is equal to reference.next. So reference.next needs to be overridden. And return start here. The thing is if we move down, we end up on an empty node and a none. I want to return back the start. But if I remove this node, so then if head dot value equals to the value, then what we're going to say is that head dot next with the start if the current value we're on is equal to if the head equals to the value, then the start is going to be overrode to head.next. And head.next is equal none. Return start. Three, four, five, six. Oh my gosh. What do you guys think? While head, if the current head value is the one we want to remove, then we say that the start is equal to head.next. So now start becomes 3. If head.value equals the value of start becomes the head.next. And head equals 2. So now we'll say elif here. So this comes true, we just return, we keep going. is getting empty lists back. Come on. While head, if the head value is equal to the value of start, goes in. Start. What do you guys think? Anybody out there have any inputs? Eating some Chester Cheetos right now. Move this. If else. Save. Ref.next equals to head. Return ref.next. So while we have values for head, if the head value is equal to the value, then the start ref.next becomes head.next, and head becomes head.next. I love head equal to the value. Next node is current next. Next node equals to current dot next. Head dot next is equals to next node. So if the say next node is equal to head dot next. If next node is none, we're going to alright, so head node is if head value, right, let's do next node. Right. Elif next node is equal to next node dot value is equal to the value, then current node dot next is equal to next node dot next. Return and then head is equal to I don't know. Yes, I think we got it. No, so attribute error none-type object has an attribute value. If next node is none, right? So if not next node, right? What are we gonna do? Break. That has to go there. All right, I'm moving on here. Let's take this. Let's go here. Shoot. I am working on Leet code number 203 and am getting stuck. Could you please coach me given my current understanding and code? Do not show me code and do not give away the answer. Looks like you're on the right track. With the approach using a dummy node to simply handle the head of the list. Okay. You're modifying head to head.next in your loop, but this would cause you to miss certain nodes, especially if you're skipping nodes. Condition for next node. You're checking next node.value. What? Okay. So where should I go? The key to fixing the issue is to make sure you're properly managing the node traversal. You need to ensure that after you remove a node, when head.value equals value, you continue traversing the list and not skip nodes unintentionally. Okay, so let's just say while head, if head dot value is equal to the value, what do we want to do? Right? So say ref is equal to the list node. Okay, so if the head value is equal to value, what do we want to do? We want to say ref dot next. So we'll say elif You've already set up a dummy node correctly to handle the case where the head might not be removed. Keep this as is. Move through your list. Instead of skipping nodes like in your current implementation, make sure that after you delete a node, you still probably update the pointers. Adjust the pointer from the previous node. We'll say while head, we'll say left equals to head, right equals to head dot next. If left is equal left dot value is equal to value, then ref dot next is equal to right. If right value equal to value, then left dot next is equal to right dot next. If right dot next if dot next is equal to none. So if the left pointer value is equal to the value, then a ref pointer moves to the right pointer. If the right pointer is equal to the value, elif, or the right value is equal to the value, if right next, then left dot next equals right dot next, else left dot next equals to none. So then at the end of this, we're going to return ref dot next if right is equal to none, if the right is equal to value, and the value after right is there, then you save it, the left to point to it. Else, it'll point to none. You break out of this loop from there. So here say head is equal to left dot next, which is right. which if right. So if right value getting blank list back still. Why I'm struggling so hard with this one. Hey C Stuff, thanks for the follow on Twitch. Now you're sitting at ref next only when you need. Find a node with a val. However, ref next should always point to the correct node as you process a list. Make sure you're updating ref next. So ref.next is equal to right. Right now you're setting ref.next only when you find a node with the value. However, ref.next should always point to the correct node as you process the list. So ref.next. Make sure you're updating ref.next even when the left value is not equal to it. Return head. So then ref.next needs to update equals to head. Put as 5. I'm trying to solve it right now, bro. It's no point in me doing your method. It really doesn't help me at all. I'm trying to learn the problem here. So stick with the return ref.next because ref acts as a stable reference to the beginning of your list, even if shit at the end. So we have to update the next ref method even if it doesn't equal. So if return ref.next. So if the right value use a while loop to go through the list. Update the list for each node that matches the value to be removed. Update the list, okay. For each node that matches the value to be removed, adjust the previous node's pointer, which is ref.next, to skip over it. Yeah, because we had to have the lagging here, right? So if we'll say if head.value is equal to the value in question, then we're going to say, okay, ref.next is going to skip over so while head left is equal to head, right is equal to head dot next. If the left value is equal to it, then we'll update it to point to the right. If the right value is equal to the value, if there's a next value, then we'll override. Else it's blank. And we need to have the ref okay, let me do this. Back it up. Previous is equal to list node, right? Previous dot next is equal to head. Okay. We're gonna have a remove node function, which is going to take in the previous and the current, and it's going to say, so we have def this here, if current dot value is equal to value, we're going to pass in the value, then we're going to say that the previous dot next is equal to current dot next, right? So if previous dot next equals to the current dot next, okay, so that's fine. So then we'll say while head, if head dot value is equal to the value, let's do this. Okay. While head, if head value equals to the value in question, then we're going to call remove node on the previous node is going to be previous, and then the next node is going to be head to remove. Okay. Well, if so while head, if the head dot value equals to the value in question, we're going to remove the node given the previous and head. Okay. And then head is going to become, so then this is going to return head dot next, and so head will become whatever's returned here, right? So then if head becomes none, it won't, so then it equals the value. So then can I just return so what happens if the current value we're on So if it doesn't equal to the value, we have head equals to head on next. What is that? None type attribute for next here. While head. Well, if head is none, why is this entering? One, two, six. Not doing anything. Oh, we need to change this equals. We'll return previous dot next, because then I get the current head given back to me. Next to get to the next value. So then blank list back. This is getting frustrating. The key is you're passing previous and head to the remove node function, but previous should move along the list with the head pointer. Move previous quickly. After checking and possibly removing a node, both previous and head should move to the next node. Previous done next at the very end. Sky, stop. Sky, stop. Sky, come here. Stop growling. Yeah, we can do that. Anshul, thanks for coming in tonight. I appreciate you, man. Hey, stop it. Stop growling. Oh, that's not nice. Stop. Why are you doing that? While head. If the head value equals the value, call. If the current value, recall, equal to right, else equal to head, and head is equal to, okay, so while head, if the head value is equal to the value, then the previous next value becomes head's next value. Perfect. Okay. Else it's not, so the previous becomes the head, and head. So in the case where it is equal to the value, you come across the 6, you're on the 6, you is equal to the value, you say, okay, previous will skip over that. Oh. What? Previous equals to this node. Previous dot next is equal to head. While head, if head value is equal to value, previous dot next is equal to head dot next. Else I don't know. This is annoying me. While current while head value previous dot next equals to current dot next. Else previous equals to current, head is equal to, and return previous next. That's what I'm doing. What are you talking about? Current is equal to head. Modifying head value. Previous moves incorrectly. When you remove a node, don't use cur alias. That's what I have. Why is it wrong? Previous should not move when you remove a node. When you remove a node, head.value equals value. Previous should not move. In your code, I have if head.value equals to value, previous.next equals to head.next, else previous equals to head. Okay, so what's the difference between these lines? Does that work? No, it's wrong. So GPT is wrong. We have a previous and a previous. I think you're really close, but you have a fundamental issue due to how you're referencing. I think you're really close, but you have a fundamental issue with how you reference it, not given away, but something you consider. The difference is what is returning between concurrent equals head, while current equals head, while current Okay, so we have a previous node that lags behind our head node. Right? So while we have a node that we're going to be iterating over, right? If I'll just say current equal to head then, like if that's what it's wanting. While current, if current dot value equals to value, then our trailer, right, is going to point to the current's next value. Else previous points to our head, points to our current, and head updates to head.next. Current.next, but that won't do anything. Hey Sticky, awesome dude, that sounds great. Hoping to get my MacBook soon so I can start learning / practicing code. What MacBook you gonna go for? Which one you eyeing? Welcome in. Thanks for the follow, CS stuff. but previous.next will still point to the last node in the list, and in this case, the first node head is removed. You'll return previous.next, which might lead to an incorrect result. So I don't want to return previous.next because I'm moving previous down. You're initializing a previous node with previous.next equals to head. Yes. This works well to handle removals from nodes after the head, but if the head itself has a value that needs to be removed, previous.next will still point to the node following. Previous.next will still point to the node following the removed head, causing issues. To fix this, you should initialize previous to a dummy node that helps in managing cases where the first node head needs to be removed. This dummy node will help make sure that the head is always returned correctly. So previous equals list node. Dude, this is exactly what I have. I have this exactly, and it is wrong. If I copy GPTs in here and I run, no way. What is the difference? Dummy equals what's that? So let me make a dummy node here. Let me say that dummy.next is equal to head. Now let's say that we have a current, we have a previous, and a current equal to head, while current, if current.value is equal to value, previous.next is equal to current.next. Else, previous equals to current. Current equals to current.next. We want to return dummy.next. Oh my gosh. Ugh. Okay, so what I was doing was I was moving my previous downward along with my previous was cascading down along. I need my previous to stay at wherever my start is. But I was using previous as I needed to create an alias for previous as dummy, and then use previous to do stuff in here, rather than keeping dummy separate. It was literally just like a couple like words difference. Yeah, we were really close, CS stuff. I don't want to break the bank since I want to switch to iPhone when a new one drops, but I'm not sure yet. What's your budget like, Sticky? Yeah, exactly. So Saye says, when you initialize a list node instance as previous, you should keep that in for return. So when I was using previous here and then also updating previous in here and then returning previous.next, my previous was iterating or was moving along with my head, and I need to return dummy.next so that my dummy node is what's returned, which points to the start or the new start of my list. So if I go back here to my previous thing here, right? So this fails, this does not work, right? Because my previous is moving along. But if I instead save previous here to equal dummy, and then I just move, I call this dummy, and then call this dummy, that's all and then make this dummy. That's all I had to do to make it pass and work. I had the actual algorithm if else statement correct, but I just had my starting condition wrong for this list node reference. Oh my gosh, dude. Literally 45 minutes of thinking that I had something wrong here when it's literally was just this here, an alias. Oh my gosh. I don't have a set budget yet. I just want a laptop that lasts for a while without worry. Yeah, that was my thing. I got for a little anecdote here. If you guys are here, part of the stream, enjoying the progress, leave a thumbs up. It really, really helps to motivate me, keep me going. Have YouTube keep, funding us to keep going here by pennies. Funding by pennies is what I mean. We don't. But I mean, it just keeps funding as in like pushing our content into the system. So thank you guys truly for being here and for hanging out with me. You guys are the best. I truly appreciate all you guys being here. My name is Michael. I have a degree in human biology and a minor in chemistry, and I work as a formulation chemist for a biotech company where I make biological controls used in patient diagnostics and testing. I have been teaching myself how to code for about 10 months now as I teaching myself through various books, resources online, and courses. I have a Discord link down below where you can get access to all of my coursework and resources for free. I have it posted in there as a roadmap that's pretty well organized, as well as other resources, and we can talk offline. So there's over 500 people in the Discord alone. We're currently working on open source courseware together, projects. I have a project I made open source for everybody to work on together, and so we're currently getting some pull requests. So we'll go over those tonight in the part 2 of the stream. But anyways, you guys, please leave a like on the stream and consider following along. We were at 18:30, so very, very successful stream today. I think we started it off at about 18:10, so 20 subs today. Thank you guys so much for all the support and all the follows over on Twitch. You guys are awesome. CS Stuff, Sticky, you guys are great. I think that part is actually the most important / valuable part of learning linked lists. I also career switched, and linked lists aren't used much in practice, but they're a great tool for learning the fundamentals of object references. What was helpful for me is drawing on paper the pointers for the linked list and seeing how the references / pointers change. Yeah, that's my difficult part is I often get my mind pretty fuzzy with what's going on, and I need to go to the whiteboard more for sure. But yeah, it's I understood the logic behind it with the pointing and where I wanted to, but I just needed to understand how to reference back to the original list with that dummy node. And I was using the dummy node, but I was altering my dummy node as I moved it through as well, and so I just needed to have a reference to it as in it itself. So kind of weird. Yeah, so Sticky, I have a MacBook Pro. So funny, so I was going to tell you is I got a MacBook Pro like every year from 2016 to 2019, and I returned every single MacBook Pro because I hated it. I built my own PCs all the way through middle school and high school. If I had bought a NVIDIA stock instead of an NVIDIA 1070 graphics card back in 2013, I would be a very rich man. So I'm a little butthurt. I didn't younger me didn't buy NVIDIA stock instead of NVIDIA 10 series graphics cards back when I was first building PCs. But that's what I was doing anyways. But I had a Red Dragon 1070 an MSI GTX 1070 GeForce graphics card on that. And so, but I bought MacBook Pros because I wanted to try it out and get into that field, but I returned every single one because the Intel chips were terrible. They just ran super hot, the fans were super loud, the software was just super slow. It was just terrible compared to my Windows machines. And then finally and then I finally gave it another shot on the M3 series. So I wanted to set a goal to learn how to program, so I made an investment and bought the 2023-2024 MacBook Pro M3 Pro, not the base Pro version. There's a base MacBook Pro. There's an M3 MacBook Pro. there's an M3 Pro MacBook Pro, and there's an M3 Max MacBook Pro. And there's on the middle tier, the M3 Pro MacBook Pro, the Pro chip. There's two versions, a less core and a more cores, and I got the more core version. So I did upgrade for the more core version on the Pro chip, not the base chip, not the Max chip, but the Pro chip, and not the base Pro chip, but the Max Pro chip, but not the Max. Gosh, the naming is so terrible. And and then I upgraded to 36 gigs of RAM just so I would be doing because I'm doing streaming, coding, watching stream YouTube, um, taking notes all at the same time. So I needed that extra RAM for my abilities. And I can tell you this right now, I've only had like one instance where my MacBook kind of got a little bit warm, like in terms of like, and that's because I was sitting on my lap with a heated blanket underneath. So I stream in 1440p, I code, I do like data analysis live on stream. I simultaneously will play music and stream music, and all of that is capable and being able to be ran on my MacBook Pro. I edit all of these videos through a Premiere Pro on this machine. It edits hour and a half videos in about 50 minutes in 1440p. It's honestly, like I said, as I returned 2016, 17, 18, and 19, I returned 3 to 4 years worth of MacBooks in a row, returned after 1 week. This one I've had ever since I bought it day one, January 1st, 2024, to start my coding journey. And I've had it ever since, and I use it every single day. It's the best laptop I've ever owned. I've had a Razer Pro back in my freshman year of college. I had a Surface Pro my junior year of college. I've had Windows machines, and by far the interactivity with the my phone, with iCloud Drive, with AirDrop, with all of that stuff, the Apple ecosystem, it's unbeatable, and it's unbeatable in my opinion. It's crazy. How do you find the portability slash battery? Dude, honest, best battery life I've ever had on a laptop. My Razer Pro always died super fast. But this MacBook, I took it to my mom and dad's house on a trip. I visited my parents, and I still streamed the whole time. And I streamed 2 nights in a row. It was a 2-day trip. I streamed 2 nights in a row and did extra coding work, and I did not charge the entire time. Think about that. And I came home at like I came home at like 30% charge. So I was able to stream for two streaming sessions for 2.5 to an hour and a half each, and do additional coding work and still have 30% battery. I can go a whole week just if I wasn't streaming without charging. I just it's great. It's a really good battery life. All right, you guys. So this was part one of today's stream. I really, really appreciate you guys being here and helping me out for this one. We started off the stream with some reading in data structures and algorithms in Python. We are currently reading this book as on stream. We started chapter 11 here on binary search trees on page 463. We're on page 485 of 770 total, so we're getting through this book pretty well. We're almost there. So thank you guys for helping me out with this. We started off with about 15-20 minutes of reading, and then we moved on and completed a few Leet code problems today, one of which being this linked list, removing elements from a linked list, and then reversing a linked list as well. I appreciate you guys joining me here for that. The part two, I'm going to take a little break, go get some dinner, and hang out and walk my dog for a little bit, and then I'll come back later this evening for our part two stream. We streamed today for a total of 3 hours and 48 minutes so far, so a good session so far. We'll come back and we'll work on our project, the thin layer chromatography simulator, where we are simulating chemistry laboratory experiments of a thin layer or a paper chromatography simulation, where you have a medium that has a polarity associated with it. You have a solvent here in black traveling up at 100% speed. Then you have random retention factors applied to 5 individual compounds, and those will grow at a rate according to that retention factor. And so you can see that this purple compound has an extremely polar relationship to the actual medium here, because it's not traveling as fast as compared to this red one, where it has like attractions of polar to polar attractions between the medium and the actual compound, and so it's able to travel along with this solvent at a similar rate. So um, Apple products are best for those who can afford them, and not many people can afford that in the beginning. Yeah, that's a good point too. Learn from video lectures. Now, I don't really like learning from lectures. I watch lectures sometimes, but I think I've been able to really progress quite rapidly in these 10 short months of coding, being able to build projects like this, starting to get it into a full front end framework here, by being able to teach myself through books, and being able to interpret English text in my own right into programming language. So by reading books, having to interpret actual English paragraphs and verbiage into code has been greatly more beneficial than kind of just honestly kind of dozing off during videos and lectures. I honestly learn a lot more just by self-teaching myself, reading books, prompting AI for examples, and really going through and making sure I understand concepts rather than just kind of watching videos. I find the videos to be pretty boring. Sticky says, good to know I built gaming PCs and a gaming laptop for college, but that laptop literally only worked while plugged in. Yeah, that was like my Razer. You had to have that thing plugged in like all the time. All right, you guys, thank you so much for being here and joining me. Please leave a like if you enjoyed the stream for part 1. I'll be back a little bit later this evening for part 2, probably in about 2 hours, 2.5, 3 hours maybe. Well, then we'll pick up and continue on, and we'll start doing the project portion of today's stream. So we'll work on continuing on with our thin layer chromatography project, where we are simulating compounds and their polarities as they move up through a solvent via a retention factor. And so our goal here is to have a user be able to, our goal is to have a user, what is it? Where's our port? Come on, come back to me. Our goal is to have a user apply their own retention factors and then generate these plots like live on the server here. And then they can also randomize the elements and whatnot. So it's going to be pretty cool. And maybe we can take it a step further and make like a whole chemistry related learning site. So cool stuff. Anyways, I'll be back in a couple hours for a part 2. I'm gonna grab some dinner and walk my dog. I'll see you guys then. Join the Discord link down below. Subscribe, like, follow the stream. I stream to both YouTube and Twitch simultaneously, so if you would like to watch on Twitch, I'm there. Links down in the description, as well as the Discord, where you can get access to all of the books, coursework, notes, projects, everything for free in my Discord.